Okay guys, in this video we are going to start Focus 17, which covers chemical kinetics. And so we'll talk about some basic ideas in chemical kinetics, and I think we'll split this topic up into two parts. So first, just kind of the basic ideas. Chemical kinetics, as you probably already know, is the study of how chemical reactions change or depend on time. And so we talk about things like reaction rates, and we want to understand how does the reaction rate depend upon the experimental conditions like concentration or the temperature of the reaction mixture. One of the objectives in chemical kinetics is to empirically deduce the so-called rate laws that can be used to then predict the time dependence of both reactants and products concentrations. And so the major objective, at least experimentally, whenever you're doing a kinetics experiment, is to be able to monitor the concentration of your reactants or your products as a function of time. And there's lots of different ways to go about doing that. The method you choose will depend upon the details of your chemical reaction, but spectroscopic methods are always a favorite. Mass spectrometry can be used, as well as slower techniques involving chromatography. For gaseous reactions, it's very common to use partial pressures as a way of monitoring the system. And in aqueous solutions, where you've got ions present being produced or being consumed, there you might look at things like the electrical conductance of the reaction mixture as a function of time. One of the caveats of kinetics experiments is that reaction rate generally does depend upon temperature. In fact, it typically increases with temperature. So while you're doing your chemical kinetics experiment, you need to be keeping the temperature constant. And there's all sorts of different technologies for doing that. I've listed a few here. You know, the common way is to immerse your reaction vessel in some sort of bath that's very large and so maintains a constant temperature. You can use so-called circulating baths that have a thermostat control, so you can, as the liquid reservoir is circulating past the system, it goes through a set of heaters that will maintain it at constant temperature. And then if you're interested in low temperature experiments, then there's special technology for doing that. You'll often be working with cryogenic liquids, or maybe you will be using techniques to adiabatically cool a gas and use that to maintain temperature control of your reactants. This example problem is illustrating pressure, monitoring partial pressures for a gaseous reaction. So we're looking at the decomposition of dinitrogen pentoxide. And what they want us to do is to express the partial pressures of each species in terms of the initial pressure of the system, which is taken to be P naught initially, and the total pressure of the system. So let's suppose that some of the dinitrogen pentoxide reacts. So at some time, the partial pressure of dinitrogen pentoxide will be P0 minus X. Then the partial pressure of the nitrogen dioxide in the system will increase, as will the partial pressure of the oxygen. This follows the stoichiometry. And as the problem says, you know, at some intermediate time, those all equal the actual pressure of the system. So what we can do is solve for x. So let's see, we'll have P naught, this is going to give us plus x plus 1/2 x. So we'll have plus 3/2 x equals P0. And so we can write x as 2/3. This looks like it would be P minus P0. So that's the value of x in terms of the pressure at some time t, and this is the initial pressure that we started off with. And so the partial pressure of N2O5 is going to be P0 minus 2/3 P minus P0. The partial pressure of the NO2 will be 2 times, so I guess 4/3 P minus P0. And then the partial pressure of O2 will be 1/2 that value of x, so 1/3 P minus P0. So these would be this is what they were looking for, express the partial pressures of the reactants and products as a function of the total pressure and P0. So you could then monitor this concentration, the partial pressure, as a function of time by monitoring the pressure as a function of time. It looks like the next couple slides are going to discuss some experimental techniques. So one of the other caveats of chemical kinetics is that your method of detection, so your method for measuring the concentration, needs to be faster than the rate of the reaction. So if it takes you a long time to do a concentration measurement, well, as you're doing the concentration measurement, the reaction may have will have changed quite a bit, and so you need, in general, you would need a method that's faster than the rate of the reaction. And so there's some techniques listed here that are very efficient for studying fairly fast chemical reactions. The first method here that we'll look at is called the flow method. Here you've got your reactants that are mixed together very rapidly around the millisecond time scale, which is a lot faster than you can pour them together. And then you analyze that reaction mixture at different reaction times, which translates into distance. Let me show you the figure here. So here you've got your two reactants, and then you've got these driving pistons that push the reactants together in this mixing chamber at a particular rate, where they mix very quickly, and then the whole system, the reaction mixture is flowing down this outlet tube. And so depending upon the rate of flow, different points along this outlet tube correspond to different points in time. And so making a measurement over here is going to give you the concentration at an early time. Measuring the concentration out here will give you the concentration at a later time. Okay, so this is called the flow method. The downside of the flow method is that you need a lot of reactants in order to maintain the flow, and so it could be quite expensive in those terms. An improvement is called the stopped flow technique, which uses a piston on the back side to control, so instead of losing all of the reactants, you pull them up, and then you have this reverse pressure, reverse hydrostatic pressure pushing the reaction mixture back. And so you would still, now what you would do is you would keep the spectrometer fixed, and then measurements at different times would then correspond to a particular amount of reaction time. So that's an improvement on the flow method. And then finally we've got an interesting method of flash photolysis. Here's where you have chemical reactions that are initiated with a burst of light, and then the products or the reactants as they react are then monitored as a function of time. I have a diagram for that here. So here's where your reaction mixture would be sitting. Got a laser beam, that is shown on the sample here. Okay, maybe this would be a pulsed laser beam or something like that. Anyway, you can also use very bright lights as well with a particular wavelength to initiate a chemical reaction. In this case, they're using a laser. the portion of the laser beam that goes through here pumps the system. That is, it initiates the reaction, and then the other half of the laser beam is then run through this continuum generator, and there's these prisms here that redirect the light, and depending upon the distance traveled will correspond to a time later after the reaction has been initiated, where you would then monitor the concentration at that time. And so by adjusting the distance, the path of the beam, you can control the time at which the probe follows the pump. And so this is a neat way to study reactions that are very fast. And so you can study reactions using more sophisticated versions that are listed here. You can study reactions that take place on the order of tens of femtoseconds. Let's see, I don't think didn't have anything else to say on this slide. So those are the three fast techniques that we're talking about. Here's a list of slower techniques. So techniques where you might want to use wet chemistry techniques to monitor concentration rather than spectroscopic techniques. And so these are called quenching methods. And so in these types of methods, you need to have the ability to stop the reaction at a particular time. And you can do that in different ways. You can do that with by adding a reactant, by adding a reagent that, say, for example, consumes one of the reactants completely, leaving the other reactant stuck or stopped at that particular time at which you added the quencher. Or you could imagine doing this by very quickly freezing your sample at a particular time. As I've mentioned already, reaction rates generally increase with temperature, so if you can drop the temperature very quickly, you can stop the reaction, effectively stop the reaction in its tracks, and then you could later analyze the sample for concentrations. Let's see here. Well, we're going to move on to the next subtopic, where we'll discuss reaction rates. Here, this slide defines the reaction rate. This is the lowercase Greek letter upsilon, which is commonly used. So it looks like a U, or maybe it looks like a V, or a combination of the two. Anyway, this is the Greek letter upsilon. And so we're using this to denote the rate. In general chemistry, usually people just write the word rate. So the rate of the reaction is this Greek letter upsilon. And in general, it's a time-dependent function. Well, I'm defining it formally here on this slide. The reaction rate is expressed as 1 over the volume of the reaction mixture times the change in the extent of reaction variable. So this is what we were looking at this variable when we talked about chemical equilibrium. And so you may recall that we were looking at plots like this. We were typically plotting Gibbs energy as a function of this extent of reaction variable. So when it's 0, we are all reactants, and then over here at its maximum value, maybe it's 1. It really just depends. That would be this would be exclusively products over here, and we were talking about equilibrium, so we were interested in the point where it bottoms out. What we're interested in here in chemical kinetics is how does this variable change with time? So how quickly do we proceed from the reactants to the products? As we have done before, you can relate the extent of reaction variable in terms of the number of moles of each species and the stoichiometric coefficient. Okay, so this is just substituting the definition of the extent of reaction in. I guess I can write it out like this, that the number of moles of any particular species is going to be equal to the stoichiometric coefficient for that species times the extent of reaction. I guess I should probably make that absolute values because I'm using the stoichiometric coefficients. the sign stoichiometric coefficients in this notation. So that gets substituted in for the extent of reaction. And so now what we can do, we can bring the volume in here, and we'll just combine number of moles with volume, and that's going to give us our molar concentration. And so this is the expression for the rate of a reaction in terms of any species I that is participating in the reaction. I'll point out that these are the sign stoichiometric coefficients, and they're negative for reactants. And for reactants, the concentration generally decreases with time, in which case you'll have a negative number times a negative stoichiometric coefficient, which is going to give you a positive rate. For products, the sign stoichiometric coefficient is positive, and the concentration of products typically increases, so you'll have a positive times a positive. Again, the rate will be positive. So by convention, our chemical reaction rates are expressed in terms of a positive quantity. And let's see, what else did I want to point out? I wanted to point out that both the extent of reaction and the concentrations of different chemical species, those change with time, right? Concentrations of reactants decrease, concentration of products increase. Also, the rate of the reaction is a time-dependent quantity. So for homogeneous reactions taking place in, say, a solution, or even in the gas phase, you can do this. The units of rate, so that is the units of epsilon here, are always going to be concentration per unit time. Typically, we use molarity, so molarity per unit time. For gaseous reactions, you still use concentration, but you use a different concentration unit. So it's not uncommon to see gaseous reactions expressed in terms of either moles per liter per second or moles per cubic centimeter per second. That unit might actually make more sense for a gas phase reaction, where the densities are lower. Here's the conversion factor between those two units. For heterogeneous reactions, which typically take place on the surface of, I don't know, a piece of metal, or the surface of a, at the interface between, between a cloud and the surrounding air, right? So reactions that take place on the surface. There, you might instead express your concentration in units of moles per area, because it's the number of surface sites, or the amount of reactant that's attached to the surface that controls the rate of the reaction. So that's not uncommon as well. And then there's nothing special about the units seconds. If you have slower reactions, it's not uncommon to see the rates expressed in terms of per minute or per hours, or per weeks. It really just depends on what you're studying. So here we're going to talk a little bit more about the relationship between reaction rates and stoichiometry. So here we'll just use this reaction right there, A plus 2B goes to 3C plus D, as a generic reaction to consider. And what I wanted to do was introduce some of the lingo that's used, and then just to point out some of the semantics around this lingo, which can be easily overlooked if it's not pointed out to you. And so what I'm talking about here in this second bullet point, the term rate of consumption. The term rate of consumption would apply to a reactant, and it's expressed as the negative of that time derivative for that reactant's concentration. So the rate of consumption of species A would be equal to minus the time derivative of the molarity of species A. Similarly for reactant B, the rate of consumption of species B would be minus dB dt. And so in this, you would expect, because of the stoichiometry, you would expect the rate of consumption of B to be twice that of species A. The rate of production refers to a product, and it's defined as plus the change in product concentration with respect to time. So for species C, the rate of production of species C would be plus dc dt. For species D, this is going to sound funny, the rate of production of species D would be equal to plus dd dt. I want you to note that the rate of consumption and the rate of production are not the same thing as the rate of reaction. They are rates, they are reaction rates, but they're not quite the same thing. The rate of the chemical reaction, so the overall rate for this reaction, can be expressed, and we'll have a separate slide on this later, can be expressed in terms of any reactant or product. And so one way you could write it is, you could write it as minus dA dt, or if you wanted to express it in terms of species B, you could write it as minus 1/2 dB dt. These two quantities are going to give you the same value for the rate, because I've taken into account the stoichiometry, right? I already mentioned that you would expect species B to be consumed twice as fast as species A. So when you're trying to calculate the absolute rate of the reaction, you need to take that stoichiometry into account. For the products, you would use plus signs. I guess that would be 1/3. And then this would be just plus dt over dt. You use plus signs because by convention we want the rate to be positive. And so since these derivatives are positive, product concentration increases, we use a plus sign. For the reactants, those are typically going to have a negative rate, and so we put the minus sign in there so that epsilon will always be positive. Okay, so this would be how you write out the rate of reaction. I'll reiterate this again later. But the rate of consumption and the rate of production, these do not include the stoichiometric coefficients. They include the signs of the stoichiometric coefficients, but they don't include the stoichiometric coefficients themselves. I may have forgotten to mention that the brackets, just like we have in chemical equilibrium, they denote the molarity of the species inside the brackets. All right. So here, this slide summarizes what I just did on the paper. So I won't reiterate it, but this is the nice clean way of writing the reaction rate. It's 1 over the sign stoichiometric coefficient times the change in that species concentration with respect to time. And for this particular example here, this is the result. Here's a graphical representation of rates of consumption and rates of production. So what you're monitoring here is the concentration of species J as a function of time, and very frequently you start off with a certain amount of reactants and no products. Okay, it's very common. What happens as time marches on? The concentration of the reactants decreases, and so you see that the slope of the line tangent to the curve is negative. Moreover, the value of the slope's magnitude also changes. Up here, you have a steep slope. Over here, you have a more gentle slope. So the time derivative itself changes with time. For the products, you've got the opposite. You've got the rate is positive, Okay, so the slope of the line tangent to the curve is positive, so the rate of production is positive. Here, the rate of consumption, you would express it as a positive number, but you need to multiply that slope by a negative sign. Okay, and that's what's exactly represented here in these two equations. This problem is just a unit conversion. It's not too critical. I'll just point it out. Right? They give you a reaction rate in terms of millimolar concentrations. So you've got some reaction rate epsilon that's equal to 0.16 times 10 to the minus 3 moles per liter per second. And you're being asked to express that in units of, oh, I see what's going on. Okay, I jumped the gun. I was thinking of a different problem. Here's what they want us to do in this one. Let's express first the rate of the reaction in terms of each species time derivative. So we're going to be using this formula, just like we did for this equation, this chemical reaction, express the rate. We're going to do the same thing for this reaction here. And so we just follow a pattern. For reactants, we use a minus sign, and we always divide by the stoichiometric coefficient. And so I'm using the first species here in the reaction. That. For the products, we'd use plus signs. And then for the bromine, the stoichiometric coefficient is 1, so 1 divided by 1 is 1. So these are the expressions for the rate. They're telling us that the rate of formation of nitrogen monoxide is this 0.16 millimoles per liter per second. They want us to calculate the rate of consumption of this reactant and the rate of production of the bromine. So rate of formation of the nitrogen monoxide means that, and it should be NO right there. What they're telling us is that this time derivative is 0.16 millimole per liter per second. And they want us to calculate this quantity. And so using this relationship right here, we see that this quantity will simply be equal to dNO dt because they have the same stoichiometric coefficients. For the bromine, however, slightly different. The rate of production of the bromine is equal to 1/2 the rate of production of the nitrogen monoxide. And so we would take that into account. Take into account the stoichiometry. And I think this is, if I'm not mistaken, oh, there is, they did want us to do the unit conversion as well. I see that at the end now, okay. And so if you had a rate equal to 0.16 times 10 to the minus 3 moles per liter per second, the conversion factor is that there are 6.022 times 10 to the 20 molecules per liter per second per mole per liter per second. So those would cancel out, and then you would just do this to get the expression in terms of, oh, and that's per centimeter cubed right there. So that would give you the number that you want here. And you could do that to all of the numbers, to all of these concentrations. Well, this is where I wanted to break the lecture into two parts, so I'm going to go ahead and stop the video right here.